wanted to do a recording to go over the key for the extra problems that I posted for molarity, stoichiometry, and gas stoichiometry. I'm going to start with problem number 1. I've already written the answers. I just wanted to go over how I went about solving them. So for this particular one, you guys don't have to be able to write this chemical equation. We didn't go over naming acids or bases for the most part. You should be able to name sodium hydroxide, sodium chloride, and water, but not so much hydrochloric acid. So the first thing I did was I just listed all of my compounds out, and then I balanced it, because for any stoichiometry problem that going forward would require a balanced chemical equation. So if you have questions about balancing, feel free to ask me during class, but I sort of just did a quick balancing. I just went through and I counted out how many of each element, and it just ends up being 1, 1, 1, 1. So you don't really have to do any additional coefficients. So after I finished balancing, I went through, and the first question is asking you, if you start with 15 milliliters of a 0.6 molar hydrochloric acid solution, how many milliliters of 0.2 molar NaOH will you need? So we are going to go from HCl into NaOH. So I know I'm going to have to eventually cross the mole bridge. So just keep that in mind. The other thing I know is that I'm working with molarity. So the first thing I do is I write down my molarity equation. Molarity is moles per liter. I wrote volume, but that volume needs to be in liters. And then I'm given 2 pieces of data for hydrochloric acid. So I plug in the 0.6 molar hydrochloric acid, and I know that I have 15 mils of it. So I do the conversion, and that's 0.01500 liters. So I've got 0.6 molar hydrochloric acid. I've got 0.01500 liters of it, and I can solve for the moles of hydrochloric acid that I have in that solution. So I solve for N, and I get 0.090 moles of hydrochloric acid. The next thing that I'm going to do is I need to go from hydrochloric acid into NaOH. I need to go from one substance into another substance. So I'm going to cross my mole bridge. And in order to cross my mole bridge, I'm going to look at my balanced chemical equation, and I see that for every 1 HCl, I'm going to use 1 mole of NaOH. So for every 1 mole of HCl, I use 1 mole of NaOH. I multiply that across, and I end up with 0.0090 moles of NaOH, because it's a 1-to-1 ratio. Now that I know how many moles of NaOH I'm going to end up using, I can then plug that into a second molarity equation, because I know the molarity of my NaOH solution. So I'm going to do the molarity of NaOH, which is 0.20 molar. I get that from the problem above. And I know that I'm going to end up using 0.090 moles of NaOH based on my stoichiometry. Then I can solve for a volume of NaOH. My volume comes out to be 0.045 liters, and then I just converted that into milliliters of NaOH. So if I were doing a titration of this acid, and I use 15 mils of a 0.6 molar hydrochloric acid, then I would need 45 mils of a 0.2 molar NaOH solution in order to neutralize it. So that's how I went about the first problem. Part B is a very similar problem, but in this case, I tell you how many milliliters of NaOH you're using, and you're solving for molarity. So you're going to sort of start off in the same place. I give you milliliters of a molar hydrochloric acid solution, and I'm asking you how much of it's going to react with your NaOH. So I am going to eventually have to go from HCl into NaOH. So I am going to eventually have to cross the mole bridge. The first thing I'm going to do is work with molarity, though. So molarity, again, is moles per volume, or moles per liter. And I know I'm working with a 0.25 molar hydrochloric acid solution. I know that I'm using 25 mils of it, which is the same as 0.02500 mils of hydrochloric acid. And then I solve for moles of HCl. So I get 0.00625 moles of HCl. Also, I did this key earlier today, so if your math comes out different, let me know. I'm pretty sure all my answers are correct. Once I know how many moles of HCl are going to react, Then I can also figure out how many moles of NaOH will also react because, again, there's that 1-to-1 molar ratio from that balanced chemical equation up here. So every 1 mole of HCl is going to react with 1 mole of NaOH. So if I'm using this many moles of HCl, then I'm going to end up using this many moles of NaOH as well. Then I can plug that back into a molarity equation with NaOH. So I'm looking for what the molarity of that solution is. I know that there will be this many moles of NaOH in that solution because that's what I just solved for. And I know that I use 10.10 milliliters of it, which is the same as 0.01010 liters. So I plug those into my molarity equation, and then when I solve for it, I find out that the molarity of that NaOH solution must have been 0.62 molar, or you could write it as 0.62 moles of NaOH per liter. So that's a couple of molarity problems. I do a couple more down here. This is very much like our scrubbing lab. So in this particular case, it's asking you how many milliliters of a 1.0 molar NaOH solution. So I'm going to end with a molarity problem. And it says that you would need to fully react with 15 grams of CO2. So I'm going from CO2 into NaOH. So that's going to be your stoichiometry. So I'm going to start with my 15 grams of CO2. And this is my balanced chemical equation up here. And I'm going to go from grams into moles of CO2. So 15 grams of CO2, you need to convert into moles of CO2. So every 1 mole of CO2 is 44.0 grams. And then in order to get to NaOH, I look at my balanced chemical equation. For every 1 mole of CO2, you're going to react with 2 moles of NaOH. So I'm going to put moles of CO2 on the bottom so it cancels. It's going to react with 2 moles of NaOH. And then what I end up finding out is that for 15 grams of CO2, it's going to react with 0.68 moles of NaOH. I'm going to stop at moles of NaOH because I'm going to use that molarity equation next. I know that molarity is moles per liter. I know that it's a 1 molar NaOH solution, so my 1 molar NaOH solution is equal to 0.68 moles of NaOH because I know that's how much are going to end up reacting. And now my question is, how many liters of NaOH was that? So I solve for V and I get 0.68 liters of NaOH, which is equivalent to 680 milliliters of NaOH. The next one continues with the scrubbing lab. In this case, it's asking you what is the maximum number of grams of CO2, so we're going to grams of CO2, that can theoretically react with 100 mils of a solution that contains 0.10 moles of calcium hydroxide. And what I realized here is that you're already in moles of calcium hydroxide, and you're trying to get to grams of CO2, so you don't even need this information over here because I'm not asking you anything about molarity for problem 3A. So what I'm going to do is I'm going to start with my 0.10 moles of calcium hydroxide. I know that 1 mole of calcium hydroxide is going to react with 1 mole of CO2. It's a 1-to-1 relationship in this balanced chemical equation. So that gets me into moles of CO2. And then it's asking for grams of CO2. So then I'm going to go from moles of CO2 to grams of CO2. Every 1 mole of CO2 is 44.01 grams. And then I'm just going to calculate it out, and I get 4.4 grams of CO2. So if you have 0.10 moles of calcium hydroxide, you can theoretically scrub 4.4 grams of CO2. All right, so then I have one limiting reactant problem. I might have done this actually before in a previous video, but I just wanted to go over it again. The first thing I did was I balanced this chemical equation. I will say this one was a little bit tricky, but in this case, I balanced my hydrogen first. I did also take notice of my number of oxygen on this side. It is an odd number to start with. And so I want to make sure that I'm always having an even coefficient here. So when I started with the number 2, it wasn't enough for my hydrogens. So then I upped it to 4. And that gave me 8 hydrogens on this side. And then I had 6 total hydrogen on this side. So then I upped my number of hydrogen on this side. So 2H2O2 give me 4 hydrogen here, 4 hydrogen here. So then 8 hydrogen altogether. And then I double checked my oxygen. So then I have 2 oxygen here times 2, that's 4. And then 4 oxygen here. So then that all balanced out. So that's how I sort of approached that balancing problem. This one was a trickier one for sure. Then what I did was, the question is asking you if you have 100 grams of hydrazine and 150 grams of hydrogen peroxide. It was asking you which one is the limiting reactant. I like to solve this problem as like a 2-part problem. There are, again, other ways to do this. This is just my preference. So I treat them as though they are 2 separate problems. So I start with my 100 grams of hydrazine and my 150 grams of hydrogen peroxide. And then I'm going to take each of them to the same product. And in this case, I'm going to choose N2 just because I ask about it in the next problem. So I go from 100 grams of hydrazine to grams of N2. And I go just across my mole map. So 1 mole of N2H4 is 32.06 grams of N2H4. Grams of N2H4 cancel. Every 1 mole of N2 is going to be created with every 1 mole of hydrazine. So it's a 1-to-1 relationship. And then 1 mole of N2 has a molar mass of 28.02. So then I calculated that all the way across and I got 87.40 grams of N2. And then I did my second problem starting with 150 grams of hydrogen peroxide. And I did sort of the same work. So 1 mole of hydrogen peroxide is 34.02 grams. In this case, it's a 1 to 2 molar ratio. So 1 mole of N2 is created for every 2 moles of H2O2 that you use. And then 1 mole of N2 is 28.02 grams. And then for the second problem, I got 61.77 grams of N2. So what I get from that is basically I can make 61.77 grams of N2 before I run out of hydrogen peroxide. Once I run out of hydrogen peroxide, my reaction will stop and no more nitrogen will be made. That means that H2O2 must be my limiting reactant. That also means that my hydrazine will be my reactant in excess. That means I will not use all 100 grams, and it also means that I will not make 87.40 grams of N2. I'm going to run out of hydrogen peroxide before I get there. So the most I can make is 61.77 grams of nitrogen. Then the next question is just asking you percent yield. So percent yield is your actual over your theoretical times 100. So if you were to run this in a lab and actually make 58 grams, and you were supposed to make 61.77 grams, you would plug that into your equation, times 100, and you would have gotten a 93.9% yield. The last couple problems on here, the next problem is another stoichiometry problem, and then it's some gas stoich. So the next one is sort of a more straightforward, just stoichiometry problem. The first thing I did was I wrote out the chemical equation. So you have ethyl alcohol reacts with oxygen gas through combustion to create CO2 and H2O. And then I went back and I balanced it. I started with my carbon and then hydrogen, and then I balanced my oxygens last because it shows up twice on this side, so I save it for last. This reaction is a combustion reaction. You can tell because I wrote it in the problem name. So, also, anytime you have a hydrocarbon reacting with an oxygen, creating CO2 and H2O, it is going to be a combustion reaction. The next question is asking you if you have 0.85 moles of water, how many moles of carbon dioxide do you produce? So it's just a one-step stoichiometry problem. So I can look at my balanced chemical equation and see that for every 2 moles of CO2, I'm going to also make 3 moles of H2O. So if you make 0.85 moles of H2O, then for every 3 moles of H2O that you're making, you will also be making 2 moles of CO2. You multiply across and you should end up with 0.57 moles of CO2. The next stoichiometry question is starting with 25 grams of ethyl alcohol. It's asking you for how many grams of CO2 you can produce. So you're going from grams to grams on your mole bridge. So you're going to start with your 25 grams of ethyl alcohol. Every 1 mole of ethyl alcohol is 50.08 grams. And then you're going to cross your mole bridge. So 2 moles of CO2 are produced for every 1 mole of ethyl alcohol. And then every 1 mole of CO2 weighs 44.01 grams. You multiply all the way across, and then you divide by everything on the bottom, and you should come out with 43.9 grams of CO2. The next problem is a gas stoichiometry problem. So it's asking you for the volume of oxygen gas that is being produced at 155 degrees Celsius and 125 kPa if you decompose 7.8 grams of calcium oxide. So you're starting in calcium oxide and you're going to oxygen gas. So again, this is going to be another stoichiometry problem where you're going to end up going from one substance into another. But then on top of that, you're working with gases at a different pressure and temperature than standard. So you're also going to be using PivNert. So I went ahead and I calculated my temperature in Kelvin, because your temperature for your gases always needs to be in Kelvin, and kPa is just fine. The next thing I did was I balanced my chemical equation, and then I started with my 7.8 grams of calcium oxide. So 1 mole of calcium oxide weighs 56.08 grams. And then I want to get into oxygen gas because that's what your question is asking about. So I also know that every 2 moles of calcium oxide is going to produce 1 mole of oxygen gas. And then I'm going to multiply across and find out that I'm going to create 0.070 moles of oxygen gas. Now, because I'm not at STP, I have to use PivNert. And my pressure is at 125 kilopascals. My volume is what I am solving for. I know my moles of O2 because I just solved for that. My R constant in this case is 8.31 because I'm in kilopascals. And my temperature in Kelvin is 428. Then I'm going to isolate V and solve for it, and I got 1.99 liters of oxygen gas at this temperature and pressure. The next question is sort of asking you a similar thing. You're just going to do the process slightly differently. It's asking you for mass of calcium metal, but you're starting with liters of oxygen gas at a particular temperature and pressure. So since you're starting with volume at a particular temperature and pressure, you're going to start with PivNert and you're going to end with stoichiometry. So I'm going to start with my PivNert. I'm at 125 kPa. I know that I've used 10 liters of oxygen gas, so that's going to give me moles of oxygen gas. I'm going to use 8.31 for my R constant again, and I'm at 428 Kelvin. So I'm going to solve and find out. Keep in mind this is moles of oxygen gas because you were in liters of oxygen gas. PivNert is not stoichiometry, so whatever substance you're in when you're in volume, you're in that same substance for moles. So it tells me how many moles of oxygen gas I have. So once I know how many moles of oxygen gas I have, then I can use stoichiometry to get grams of calcium. So for every 1 mole of O2, I am going to use 2 moles of calcium. That is in my stoichiometry, my balanced chemical equation above. So every 1 mole of O2 is also going to produce 2 moles of calcium. And then for every 1 mole of calcium, it weighs 40.08 grams. So that's going to calculate out to 28.1 grams of calcium. So if 10 liters of oxygen gas do react at this temperature and pressure, you will end up also creating 28.1 grams of calcium metal as well. All right, the last question is a gas limiting reactants problem. And in this particular case, you're going to use your mole to mole ratio as a liter to liter ratio. So it says that you are at a high temperature and pressure, but it doesn't tell you what the temperature and pressure are. But if you look at the top of your mole map, if your temperature and pressure are not changing, your mole to mole ratio can also be a liter to liter ratio. So in this particular case, you have 4.5 liters of carbon monoxide reacting, and you also have 8.25 liters of hydrogen gas reacting, and it's asking you basically which of those is going to limit your reaction. So which of those is going to limit the amount of methanol that you can make. So in this case, again, I treat it as two problems. So I'm going to start with my 4.5 liters of carbon monoxide. And what I did was I did my balanced chemical equation beforehand. So carbon monoxide is CO, hydrogen gas reacts with it and creates methanol. And then I balanced my hydrogens. And then once I balanced my hydrogens, everything was balanced. So when I look at my balanced chemical equation, for every 1 mole of carbon monoxide, I also make 1 mole of methanol. So technically, if you're at a constant temperature and pressure, 1 liter of carbon monoxide will also make 1 liter of methanol. So if 4.5 liters of carbon monoxide are used and it's a 1-to-1 ratio, then I will also make 4.5 liters of methanol. I'm going to do the same problem, but with the hydrogen gas. I start with 8.25 liters of hydrogen gas, but in this case, it's a 1-to-2 ratio. So every 1 mole of methanol requires 2 moles of hydrogen gas in order to produce it. So 1 liter of methanol would also require 2 liters of hydrogen gas in order to produce it. So again, if your temperature and pressure aren't changing, your mole to mole ratio can also be in liters. You could also technically use 22.4 liters for this and go to moles. Your answers will come out the same. It's just one extra step. So I do my liter to liter ratio, and then I find out that 8.25 liters of hydrogen gas can only make 4.125 liters of methanol. And so since my hydrogen gas can only make 4.125 liters of methanol, that's the most methanol you can make. Because at that point, you're going to run out of hydrogen gas. Once you run out of hydrogen gas, your reaction will stop. Your reaction will stop at 4.125 liters of methanol. You will not use all 4.5 liters of carbon monoxide, so that's your reactant in excess, and you will not make 4.5 liters of methanol. So that's just sort of how I went about these particular problems. If you want to go over them some more, just stop by the office and I can meet with you and talk to you about these problems.